Hello everyone, today we're going to talk about Retrieval-Augmented Generation, which is a very well-known pattern when you do generative AI. And we'll focus on something called EasyRAG from LangChain4J. And we'll see that in just 10 lines of Java code, we can build a RAG-based Java application. That seems very easy. Well, 10 lines of code is small, but also it's quite complex if you go into the details. So the goal of this session is to have a look at those 10 lines of code, understand how they work, understand some best practices, how you can improve them, so you can have very quickly a RAG-based application in Java. I'm Julien Dubois, I work for Microsoft in Java Developer Relations, and I'll be your guide for today. So, what is LangChain4J? LangChain4J is a now well-known project in the AI world in Java. It's a port of LangChain, which is a Python and JavaScript library. The goal of LangChain4J is to help you use large language models in Java, and that's exactly what we're going to do today. And it's fully open source, built by a community which is very dynamic. I'm part of it, but lots of other people are also contributing. And if you wish to do more with LangChain4J, don't hesitate to join us. It's a very open and nice community to advance AI in Java. Now, why do you want to use LangChain4J? It's for three reasons. The first one is that it gives you a layer of abstraction on top of many APIs. Typically, when you access an LLM, like Azure OpenAI, well, you need an SDK for this. And LangChain4J gives you an abstraction layer on top of all those SDKs. So it makes you more productive faster, but also it helps you use one LLM or another one or a vector store much more quickly, and you can change them depending on your needs, which is what you will want to do when you will start using them. It gives you lots of tuning, nice integration on top of all of those, and that's exactly what we're going to do today with the RAG pattern. The RAG pattern is basically going to need access to different LLMs and to a vector store. And if you want all of this, well, you can do everything by hand, of course, but it's very cumbersome. Here you will see with the EasyRAG pattern from LangChain4J, everything is made up for you. Everything is already well suited, and you will gain a lot of time and a lot of code by using this. If you want to do the demo that I'm going to do right now, you can go to GitHub here. There's a QR code, there's a link. And this is a pretty complete demo. We'll focus here on part 10 and 11 of the demo, where we ingest some data and then we use a RAG pattern to get some answers from our LLM. So what is RAG? What are we going to do? So RAG is Retrieval-Augmented Generation. The goal is to fix two of the main limits with LLMs when you do generative AI. The first issue is that they have a cutoff date. They were trained like 2 years ago, so they don't know what happened last week. And they also are trained on public data, so they don't know internal company data. So if you ask them, what's the refund policy in my company that was published last week, it has absolutely no idea, and it will just hallucinate and made up some stuff. So you want to fix those two issues, and there are different ways to do that, but the typical way using RAG is to get that data, that new data or that private data from somewhere, transform that data into a vector that you will feed into a vector database, and then use that vector database to get similar data and add some more context to your LLM. So when your LLM answers you, it will use that data to answer you with more information, like recent information or private information. It looks a little bit complex, but again, that's what we're going to do in the next 20 minutes. And this is where LangChain4J is really good at. LangChain4J has got, let's say, connectors to a lot of LLMs, a lot of vector stores. It's got libraries to help you do RAG. So all of this will be very easy with LangChain4J. So let's do it. Let's take the code. Let's open it in IntelliJ and have a look at how it works. So here's the code. The first thing I'm going to do is run everything inside Docker. So we've got, if you go to the README, we've got different ways to run this application. We're going to use option number 2. Everything runs locally, but it's not very good. The idea is to have something fast and small so that we can run here easily for our demo, but it's honestly not very good. So if you want something better, for example, you can use option 3, where you need let's say a better laptop, you need a GPU and everything if you want to have some good results. But honestly, option 2 is enough to test and go fast. So that's what we're going to do right now. So for this, I'm going to run everything inside Docker. We're going to use basically 2 tools. We're going to use LangChain4J, which is a tool that runs LLMs inside a process that's here inside Docker. And we're going to use Qdrant, which is a vector database. All of those can be easily switched thanks to LangChain4J. Again, it's got connectors for lots of other LLMs, other tools, and other vector stores. So very easy to change everything. Here I'm using those because they are small, fast, and easy, which is my goal for a demo or for testing. Probably that's not what I would use in production, but we'll talk more about production in a bit once we have everything running. Once I have everything running, so we're going to basically focus on 2 parts. One part where we ingest some data, and then another part where we use that data to get some information. So let's go back to the slides and explain a little bit more about what's going to happen. First thing we're going to do is ingest the data, and that is done in several steps. That's the most complex part. So first of all, you need to get the data. You can get it from a URL, from a blob storage, from a GitHub repository. There's different ways to get data with LangChain4J, or you can also code your own data loader by hand. Once you got the data, very often you need to transform it to get only the text. Here, what we're going to use is a URL and some HTML data. And so you will want to get the text out of that HTML file, so you need to transform it. The third part is splitting the data into segments. That's honestly the hard part. You don't want to have all the data sent to the LLM because, like typically in the example we will have here, it's something really big. And so you want to split it into meaningful segments. And what is a meaningful segment? Well, it depends on your data. Very often it would be paragraphs, it can be lines, it can be sentences, it can be words. Well, words might be a bit too small, but I mean, how do you decide? Well, you decide depending on your data. Or here, you can trust LangChain4J. We've got some defaults. So the algorithm we use is called recursive. So it's going to try to fit the data you want into a paragraph. If the paragraph is too big, it will use a line. If the line is too big, it will use a sentence. So it's going to try to have a meaningful segment of data that fits into the size that you tell it that you want. And you have 2 sizes that you can set up here. There's a segment size. So how much data do you want? Like 300 characters, which is what we're going to use. And the overlap size. So you're going to have different segments. And you want some overlap often between 2 segments because there's some interesting data before and after. And here we'll use the default settings of 30. So we'll have a segment of 300 and an overlap of 30. And we're going to try to split our data into paragraphs or sentences. A nice tool to help is this one, LangChain Text Splitter Streamlit.app. I've already loaded it here. That's a playground, so you can have a look at how your data will be split. That's done with LangChain, not LangChain4J. So that's the real original Python tool. By default, they're splitting stuff with 1,000 characters and a 200 overlap. I find this is a little bit too big, but depends on what you're doing. And you can put some text here and have a look at what it's doing. So I'm going to take the text here. So that's a lot of text. Put it here. And I'm going to ask it to split that text. And so it's going to split it into segments of 1,000 characters with 200 overlap. Come on. Here it is. So those segments, I believe, are a bit too big. But I mean, it can work. The ones we'll use with LangChain4J is 330, which is much smaller. Sorry, 30. Well, let's skip 60. Probably not going to hurt a lot. And as you can see here, I've got much smaller segments. And we're trying to have sentences. Sometimes it works, sometimes it doesn't. It depends on the size. That's the default that is commonly used with LangChain4J. But again, it depends totally on your data and what you want to do. You should have segments which are as small as possible because you don't want to send too much stuff to the LLM. If you send too much data, it will overload it, and you will have some bad results. So it's not good to send too much data. Also, it costs money to send that too much data, so that's not good. But you also don't want to send too little data. If you don't send enough data, it will not have the context to answer you correctly. So there's a balance, and here's some good test and discussion to do. But again, there's some tooling to help you. And the defaults are pretty good. So you got the data, you transformed it into text, you split the data. The next step is to transform it into a vector. That's what's being called here an embedding model. So the goal is to take that segment of text and transform it into an array of float. So an array of float is like, here I gave an example of an array of float with a few dimensions. What's going to happen here is that we're going to use a lot of dimensions. Very often you use 1,568 dimensions. So we're not in a 3D world like our world. It's a world with a lot of dimensions. And the goal here is that you've got some specific LLMs which do that embeddings. So they were trained with a lot of data. And when you give them some text, they will calculate the array of float that point to the same direction as your data. Let's take an example. I'm taking apples, bananas, strawberries. They all point in the same direction as a fruit. So when somebody will ask, oh, I would love to have fruits, it will give you, oh, well, apple, bananas, and strawberry, they all have fruits because they are all pointing in the same direction. Of course, with 1,568 dimensions, you've got lots of directions for lots of different meanings. The more dimensions you have, the bigger the model you have, also the best answers you will get, but also the slowest it will be. There are many of them. I'm listing here a few of them. Some are better than others depending on the tasks that you want. So some are good at understanding code, like Java code. Some can understand other languages, like Chinese. So it really depends on what you want to do. So there's a lot of work here to take a good one. Those are good ones for, let's say, English text, and they are quite generic. So those models are themselves LLMs and will be used to transform your segments of text into array of floats, so into vectors. When you've got those vectors, you want to store them, and you will store them in a vector database. This is what we call an embedding store. There are different ones. They are not all vector stores, or they are often vector stores with added features like full text search, so they can find those vectors better than just by doing a vector search. But for starters, here we'll use a vector store, which is the classical way to do this. So in the vector store, you're going to store all your vectors, and you're going to store also some metadata. So there's one metadata you want absolutely, it's the text itself, otherwise you will have lost the text. And you need that text, of course, to feed it later to your LLM. You usually want to add more metadata, like some reference, like the document where you found the data. It's usually a good practice to say, oh, this is my company policy to do this thing, and here is the reference to the file where I saw it. So it's usually a good thing to add more metadata than just the text. And the good thing with vector stores is that they are very fast and very good at finding similar vectors, so vectors which point in the same direction. There are different algorithms for this, but the most common one is cosine similarity. So it's just calculating the angles to see which vectors point to the same direction. To put this in a graph, so what we have just seen, so you take a document, you split it into segments. So segments are transformed into embeddings, so into vectors, and then you feed those vectors as well as the original text into an embedding store. Seems easy. Well, here is how it's done with LangChain4J, and we're going to execute this in a few minutes. So here we're going to take some data from a URL. It's the Microsoft Investors Annual Report from last year, so it's pretty recent. Probably your LLM was not trained on that data. That's new data. That's interesting to get. We're going to pass it. First thing is taking the HTML coming from this CSS class. Then we're going to split it, as we said. So we use the recursive splitter with 300 characters per text segment, with 30 characters of overlap between two segments. We'll use an embedding model to transform this into vectors, and we'll store it into an embedding store. Well, let's have a look. Here is the code. I just wanted to show you more about the embedding model and the embedding store. So in that demo, we've got in the configuration package, we've got different embedding models. So we're going to use Mini-LM, which is a very small embedding model, which is right here. So it's working inside Java. It's Java-based. It's fast. It's good enough, but probably not enough for production. So you've got better ones here. For example, with Llama, you can use nomic embedded text. With Azure here, we're using text embedding ADA. There are different ones. Again, here for small tests, we're using this one, which runs inside the JVM because it's faster and easier. So that's the embedding model we will use. And then we're going to store everything into a vector store. So we've got two examples here. We're going to use qdront. Qdront is a nice and fast vector store that can run easily inside Docker. And so we're going to use it to store all our vectors. As everything is already running, just wanted to show you qdront. So this is the UI from qdront. It's empty at the moment. We have no data. And we're going to feed the Microsoft annual report into qdront. So let's do this. Let's start the app. Here it is. And let's connect to it. Here it is. So we're going to do demo 10, advanced data ingestion, and let's have a look at the logs. So what it did here, it took the document, splitted the document into 1,563 text segments. So again, we took like small segments, transformed them into vectors, and fed all those vectors into our embedding store. That was pretty fast. Again, here we're using small embedding models. We're using everything we can do to go fast. They might not be perfect, but they're good enough and they're very fast. So, okay, well, let's have a look at the qdront UI. If I refresh it, so now we've got our index with 1,563 vectors. If we open it up, we can see some of those vectors. Well, let's take, I don't know, load more. Let's take something a little bit interesting, like this one, I don't know. So this is the text. So that's the segment. The vector is here. You can have a look, like it's just a big array of floats. You've got some metadata, typically the URL where you got that data. And you can, well, here you can play with it, like you can find similar vectors. So segments in those 1,563 segments that point to the same direction, so similar segments. If we say find similar, it's going to find, well, normally segments which are similar to that one. Some best practices we've just seen. You need to clean up the text. You need to have some nice text. You need to split that text into segments, and you need to test that. You've got different ways to split that data. You've got different segment size, overlap size. That's some work to do. There are different embedding models, and all of them can have a maximum number of dimensions, but you can lower that number of dimensions to have something faster, but of less quality. Lots of tests here if you want something which is of good quality and which is fast enough. And that depends on your data also. So that's what you need to do. You need to use some metadata, at least for quoting the resources or having the text that you want to show. So metadata is really important. And you need to be ready to reindex everything because, as we just said, you want to play with that data. You want to split it differently. You want another embedding model. You want more dimensions. If you want to do that, you will need to reindex everything. So you need to have that batch of data ready to get reindexed very often. And anyway, as one of the goals here is to have recent data, you will need to index new data regularly. So you need to plan this. My advice here is to have a small set of data for testing, so you can test very often if, well, your process is working well or if you can improve it. So that's really something that you don't do once. It's something that you need to use regularly and improve regularly. Also, you've got new models all the time, you've got new data. So there's work here to do to maintain this, to have some good quality data coming to feed then your generative AI process. Now we've got the good quality data. Well, we want to use it into Retrieval-Augmented Generation. So we're going to get typically user's question. We're going to get a question. The question we will ask in the demo is how many employees are there at Microsoft in the US? So that's the question we have. You want to transform that question into an embedding. So the same process we just did before, we transform it into a vector. Same vector as, same type of vector as the ones we just did before. So same embedding model, same number of dimensions. So we can ask the vector store, which vectors are pointing in the same direction as our question. And it's going to find for us similar vectors. There are different ways to do this. The basic way to do this is to, again, use cosine similarity and find similar vectors. There are more advanced solutions, like typically using Lucene, so doing full text search, and then having calculation to see which of those different search engines is doing the best scoring, so you can find the best similarity documents in the end. The goal here is to have a limited number of segments, a limited number of documents that match what you are looking for. You don't want to have tons of them, otherwise the quality will be really bad. You want to have a small number of them which are very good. And so there are different ways to find better text segments. But yeah, the most, let's say, common way and easiest way to do is what we're doing right now, doing a vector search. Once you've got those text segments which are similar to the question you asked, well, you're going to ask your LLM, so you're going to ask your AI system a question, well, the question that the user had, but you're going to augment it with the text segments you add. You're going to add more context. That's the whole trick about Retrieval-Augmented Generation. You're going to find more context and add that context to the question of the user. I'm giving you here some examples of, well, say, well-known LLMs. So GPT-4o and GPT-4o Mini are the latest and greatest from OpenAI, so they're supposed to be the best ones. If you want to have a smaller one and still a good one, that's Phi 3.5 from Microsoft. It runs easily on a machine if you have a GPU. That's not what I'm going to use right now because I'm using my GPU to film and I don't want my video to have lower quality because the LLM is using the GPU also. So they get into some kind of competition. So maybe you want something smaller, even smaller than Phi 3.5 if you can't use the GPU like myself or if you don't have one. There's two small models which are well known. There's Llama 3.2, which was released very recently. It's very small. It's from Meta. It seems to be very good, but you cannot use it in Europe. So I cannot use it, and I don't know if it's as good as it's expected. And then there's TinyLlama, which honestly is not really good, but it's incredibly small and fast. And for doing a demo like this, that's wonderful. And we'll see it's probably going to be good enough to answer us. It will hallucinate a bit. It's not always perfect because it's very small. But for doing a demo like this, it's enough. And it doesn't consume a lot of resources, which is, of course, really cool. When you do RAG, so what we just said is that you have the user question and you augment it with some text information from our vector store. That's how it works by default with EasyRAG from LangChain4J. So this is the prompt that we have by default. You've got the user question, then there's answer using the following information, and then you've got those text segments. You can improve that. I personally like to be a little bit more directive into my question. I'm usually telling it, don't answer with any prior knowledge, so don't use the data you were trained on, but only use the data that is below. Only use the facts that are into these text segments. And also, if you don't know, well, tell that you don't know, because one of the issues with LLMs is that they tend to hallucinate. So if they don't have the data, they will make up some fake data. And I don't like this. So I'd rather tell it, if you don't know the data, if you don't know the facts, well, tell me that you don't know. I'd rather have an honest answer. So you can improve that prompt if you want to, but that's the default prompt from LangChain4J. And honestly, it's going to be enough for our test. So now, again, a graphical representation of what we just discussed. So the user is asking a question, is having a query. You transform it into a vector. You send it to the embedding store that's going to find relevant segment of text related to your query. Then LangChain4J is going to merge the user's question and those text segments into a big prompt, and it's going to send that prompt to our large language model. So in our case, to TinyLlama, and we'll get an answer. Here's the code. So the question is, how many people are employed by Microsoft in the US? And you can see that you ask a chat language model that question, and you add data by using a content retriever, and our content retriever takes the data from an embedding store using an embedding model, and the number 3 at the end is the number of answers that you want. So here we're going to have 3 text segments. Again, we don't want to have 300 text segments. If you have too many of them, it will just send too much useless data to the LLM, and you will have a very, very bad answer. Typically here with TinyLlama, the answer will be horrible. You want to have a limited number of text segments which are sent back, but which are very good. And that's the goal of what we're doing here. Let's go to the code and well, test this for real. So again, here is the question we're going to do, and let's read it. Here, so it's demo 11, and we can see here in the log. So what it did is that it got the text segments which are similar to our text segment from Qdrant, and it used, it sends that data here to TinyLlama. That was very fast. It sends that data to TinyLlama saying, so this is my question, how many people are employed by Microsoft in the US? And then LangChain4J added the prompt that we just saw before, answer using the following information, and here are the 3 text segments that are relevant to our question according to Qdrant. And then we got the answer later. Well, let's have a look at it graphically. And there are 221,000 people at Microsoft, but in the US, it's 120,000. So the answer is good. It's not, honestly, it's not perfectly good. I would have loved it's 120,000 people, not have those other information, but we got we got the correct answer. So again, TinyLlama is good enough for answering this. If we ask it again, and so this one is a little bit better. And again, 120,000 people are employed by Microsoft in the US. So again, here we don't have extremely good embedding models or chat models to answer us, but that's enough for doing a test. And if you want something better, well, have a look in our sample here. We've got some better models, from chat and better embedding models. So some best practices that we've just seen, do not send too much data in the prompt. The answers will be really bad, and it will also cost you more tokens, so it will cost you more money. So you need to be careful at sending it just the right amount of data, not too much, but also not too little data. You need to test everything. There's lots of chat models. Some of them are better than others, depending on the task and also depending on the training data. Usually bigger models cost a lot more money. So only use them if they are useful. Here, for something as simple as what I'm doing, TinyLlama, well, is good enough. Maybe, I would use something a little bit better like Phi3, but why use something bigger, which would be more expensive and slower? Well, it's probably not a good idea to use a better LLM for something like this. So depending on your task, well, have a look at what models are good and what are the pricing. If you want to improve also your results, you can improve the prompt, as we just saw. Be careful, the prompt also depends on the model. The models don't always react the same way depending on the prompts that you use. So maybe a prompt that will be good with one model will not be good with another model. So there's work to do here. And if you want to be sure that all of this works correctly, because that's pretty complex, you can add integration test. Well, just let me show you my integration test here. If I go to test, demo integration test. So I'm using TestContainers here. So TestContainers here is running a Docker Compose file where there is a Qdrant and Llama configured. And it starts everything into Docker, waiting for everything to start. And once everything has started, well, I can use a EasyRAG, so I can ingest my data. Here I'm querying my demo number 10 like we did. So the answer is okay when you ingest everything. And then you query the data with the demo number 11 that we just did. And you remember the correct answer is 120,000 1,000 people employed by Microsoft in the US. So just by doing this, I can have integration test that is having a look that my ingestion process and my RAG process are working correctly. And that's very useful because, again, you will want to improve those and on them very often. So there is clearly work to do here. Last but not least, we did everything on my laptop only using a CPU and running inside Docker. If you want something better, you will need GPU. This is extremely slow if you don't have a GPU. I mean, if you use a good model. So in production, you have no choice. You will need to use GPU. And well, that's something to be aware of because they cost money, they are hard to find. So you have some services like Azure OpenAI that provide you with all those models running already in the cloud with good GPUs. And I mean, and that's why they are so popular today. Putting it all together, so what we've just seen, we've seen that EasyRAG from LangChain4J makes it very easy to use the RAG pattern in Java. You've got lots of sensible defaults, you've got lots of tooling. Everything is ready for you, so you can have it running in just 10 lines of code. So if you just follow this tutorial, you can have everything in the next hour. It's also easy to extend, as we just saw. You've got lots of models, lots of tunings. Everything is ready inside LangChain4J for you to modify, tune, enhance this process, so you've got better results for your data. Again, thanks to LangChain4J, you can have your RAG-based application available in no time, and that's wonderful. But then, as we just discussed, you'll need to improve the ingestion process, you will need to test lots of LLMs, there's lots of tuning, and that will cost you a lot of time and money, as AI is not replacing your hard work yet. That's not something AI can do yet. It's you who needs to understand how AI work and how you can benefit from it. If you're interested by all of this, we've got another demo. That's not the same one as the one we did. That's a full demo. That workshop is about 3 hours long, maybe 2 hours if you're really fast. Here you build everything from scratch, so you still use LangChain4J, but you don't use the EasyRAG part of LangChain4J. You do it manually, so you understand everything much better. It's very interesting if you want to have a better understanding of the tuning and the enhancements that you can do with EasyRAG. And again, it's going to take you about half a day to get the full picture. I hope you enjoyed this little demo. See you soon.